Someone has compressed the whole of English Wikipedia down to 11% of its size. Not a summary, not a selection, every byte recoverable. Exactly. To get there, the program had to learn how sentences end and what follows the word therefore, and enough physics that a paragraph about thermodynamics stops being a surprise halfway through. The people who run that competition do not regard that as a side effect of good engineering. They think it is what intelligence is. That sounds like the kind of claim you would want to argue with, and it is worth saying immediately that it is not a slogan. It is a theorem, or rather a short stack of them, and by the end of this you will be able to see exactly where the equal sign goes and exactly where it stops. The route runs through 4 ideas: information, entropy, compression, and the length of the shortest program that could have produced what you are looking at. Start with the smallest version of the problem I can put in front of you. 2 strings, 30 bits each, so they cost precisely the same to write down. One of them you can continue without being told anything more, and the other you cannot, and no amount of staring will change that. Everything in this video is an attempt to say what that difference is, in a way you could compute. Start with a single event. If I tell you something you already expected, you have learned almost nothing. If I tell you something you thought was nearly impossible, you have learned a great deal. So whatever information is, it should grow as probability shrinks. This is not a metaphor about feelings of surprise. It is a constraint on what the function can look like, and together with a requirement that independent events add, it pins the answer down almost completely. There is essentially one function that does this properly. Information equals minus the logarithm of the probability, base 2, so the unit is the bit. An event of probability 1/2 carries 1 bit. 1 in 1,000 carries just under 10. Certainty carries 0, which is the whole idea. A thing you already knew tells you nothing. The additivity is the reason for the logarithm specifically. If 2 independent things happen, their probabilities multiply, and we want the information they carry to add, which is precisely the property a logarithm has. Now average that over everything the source might do. That average is called entropy, written H, and it is the expected surprise per symbol. A fair coin sits at exactly 1 bit. A coin that lands heads 9 times in 10 sits far lower, because most of the time you were right. Entropy is therefore not a measure of how complicated something looks, but of how much you do not already know about what it will do next, averaged over everything it might do. Here is that number computed rather than asserted. 9/10 times the surprise of heads, plus 1/10 times the surprise of tails. Under half a bit. The coin still has 2 outcomes, but it is carrying much less than 1 bit of news per flip. And this is the first place the whole framework earns its keep, because that number is not a summary or a score. It is the exact rate at which the source is producing news, in units you can spend. And now the part that turns this from a definition into a constraint. Shannon proved that entropy is a hard flaw on compression. No code, however clever, can represent that source in fewer than h bits per symbol on average. Not a rule of thumb. A theorem. The theorem cuts in both directions, which is what makes it useful rather than merely discouraging. You cannot do better than h, and you can always get arbitrarily close to it given long enough blocks to work with. You can watch the flaw being approached. 4 symbols with these probabilities. Give the common one a short code and the rare ones longer codes, and the average length lands here. The entropy of that distribution is here. The gap is small, and it is provably never negative. The reason shortcodes must go to common symbols is now arithmetic rather than intuition. Every bit you spend on a symbol is paid once for each time it occurs, so the cost of a code is its length weighted by how often you use it. What happens if your model is wrong? You still assign code lengths, but you assign them by the wrong probabilities. Shortcodes go to things that do not actually happen often. The average length rises, and the amount it rises by is exactly how wrong you were. So a model is not scored on whether its story is pleasing. It is scored in bits, against a floor set by reality, and the penalty for being wrong is a physical quantity you can measure on a disk. That quantity has a name, and if you have trained anything you have already minimized it. Cross-entropy, the expected code length when you encode a true distribution using a model's probabilities. It is the loss function of every language model in existence. Training a model on next token prediction is training it to compress. This equivalence is not a way of thinking about training. It is what the loss function computes, line by line, and the number printed during a training run is an expected file size measured in nats or bits. And I mean that literally, not as an analogy. Arithmetic coding takes any predictor that outputs probabilities and turns it into a compressor whose output length is minus log 2 of the probability the model assigned to the actual data. A better predictor is a shorter file. The same object measured two ways. There is no approximation anywhere in that correspondence, and it runs in both directions. Any compressor also defines a predictor, because the lengths it assigns are probabilities in disguise. So put a real source through it. 26 letters chosen uniformly would carry log 2 of 26 bits each. English does not. Shannon ran experiments on human subjects in 1951 and put printed English between 0.6 and 1.3 bits per character. That drop, from 4.7 down towards 1, is the measurable trace of everything English has that a uniform alphabet does not. Spelling, grammar, idiom, and the fact that sentences are about things. There is a standing prize for pushing that number down on real text, 1 billion bytes of Wikipedia. The record compresses it to 110 million, which is 0.886 bits per character, inside the range Shannon estimated from people, and below his midpoint. What makes that number remarkable is not the engineering, but what it implies. To get there, a program has to have absorbed an enormous amount of ordinary knowledge about the world, because that knowledge is what the remaining redundancy consists of. The prize exists because of an explicit claim that compressing text well and understanding text are the same problem. To predict the character after a sentence about physics, you need to know some physics. There is nowhere else for the bits to come from. And the argument is hard to escape because compression is one of the very few tests in this field that cannot be gamed by memorization. The compressed file plus the decompressor is the whole submission, and any memorized table has to be paid for in bits. But entropy has a hidden requirement, and it is a serious one. Entropy is a property of a distribution. It needs a source, an ensemble, a thing that could have produced other outputs. Point out one particular string and ask how much information is in it, and Shannon has no answer. This is a genuine limitation rather than a technicality. Most of the objects we actually care about arrive exactly once, with no ensemble behind them and no meaningful way to ask what else they might have been. Kolmogorov's answer was to stop talking about sources altogether. The complexity of an object is the length of the shortest program that outputs it and halts, not the shortest description in English. The shortest program on a fixed universal machine. Fixing the machine matters less than it sounds, because any two universal machines can simulate each other with a fixed size interpreter, so the complexities they assign differ by at most a constant that does not grow with the object, which is exactly the tool the two strings needed. The first has a short program, print 01 15 times. The second has none better than print followed by the string itself, same length on the page. Different lengths as programs. The second string admits no such program, not because we have failed to find one, but because, as we are about to count, almost no string of that length can possibly have one. And notice what changed. We are no longer asking what a source tends to emit. We are asking what this object is on its own. Randomness stops being a statement about where something came from and becomes a statement about how short its description can be. That shift is the reason Kolmogorov complexity keeps appearing in arguments about intelligence. It lets you talk about the structure of a particular thing in front of you, rather than about a hypothetical population it was drawn from. Now a counting argument, which is the most useful thing in this video, and you can check every step. How many strings are there of length n, 2 to the n? How many programs are there shorter than n bits? At most 2 to the n, minus 1. Every program shorter than n bits is a binary string shorter than n bits, and the number of those is 1 less than 2 to the n, summed over all the lengths below it. So the programs run out before the strings do. At most, one string in 2 to the k can be compressed by k bits or more. Save 10 bits, and at most one string in 1024 qualifies. Save 20, and it is 1 in a million. This is not a statement about our cleverness or about any particular compressor. It is a fact about how many short things there are, and no algorithm, present or future, can get around it. Which means almost every string is incompressible, and almost every string is therefore random in Kolmogorov sense. Structure is the rare case. The sequences you can predict are a vanishing fraction of the sequences that exist, and intelligence only ever operates on that fraction. The interesting consequence is not that randomness is common, but that structure is expensive. A universe in which prediction is possible at all is a very unusual corner of the space of possible sequences. Here is where it stops being usable. Kolmogorov complexity is not computable. There is no program that takes a string and returns the length of its shortest program. If there were, you could use it to build a description that describes itself as too long to be described, and the contradiction closes. The proof is a formalized version of an old paradox about the smallest number not describable in fewer than 20 words, which is itself a description of that number in fewer than 20 words. So every practical compressor is an upper bound. Whatever length it achieves, the shortest program is at least that short. You can always demonstrate that something is compressible. You can never demonstrate that something is not. This asymmetry is worth holding onto, because it is the shape of essentially all empirical work. Evidence of structure is obtainable, and proof of its absence is not. Solomonoff took the same idea and pointed it at prediction. Consider every program that reproduces the data you have seen. Weight each one by 2 to the minus its length. Let them vote on what comes next. Short programs get most of the vote. The weighting is the whole content of the method, and it comes from a simple observation. If you were to choose a program at random by flipping a coin for each bit, a program of length L would arise with probability 2 to the minus L, which is Occam's razor, written as arithmetic rather than advice. Simpler explanations are not merely preferred, they are more probable by an amount you can compute, because there are fewer short programs and each one carries more weight. And this resolves an old complaint about Occam's razor, which is that simplicity seems to be in the eye of the beholder. Fix a machine, and it stops being a matter of taste and becomes a number. And it works, in a provable sense. For any computable source, Solomonoff's predictor converges on the truth, and the total error it makes before getting there is bounded by the length of the shortest program for that source. It is the best predictor that can exist. It is also uncomputable. Those two facts sit uncomfortably together, and most of the last 60 years of this subject is an attempt to buy back computability by giving up some of the optimality. Add decisions and you get the last piece. An agent that uses Solomonoff induction to predict and picks whichever action maximizes expected reward across all those weighted hypotheses. Hutter called it AIXI and proved it optimal in a precise sense. The theory is clean enough that you can prove things about it and useless enough that nobody can run it, which is a combination worth taking seriously rather than dismissing. So the mathematical answer to the question is available, and the pattern in it is hard to miss. Optimal prediction is compression. Optimal action is prediction plus arithmetic. And every one of these objects is uncomputable. The uncomputability is not an accident of these particular definitions either. It follows from the same source each time. The moment you quantify over all programs, you have quantified over programs that do not halt. Which is not a footnote, it is the entire subject. Drop the requirement of optimality. Add a budget of time and memory, and you get everything that actually exists. Every animal, every algorithm, every model. Intelligence in practice is what approximation under a budget looks like. And once resources are in the picture, the questions change shape entirely. Not what is the best model, but what is the best model you can find with this much compute, on this much data, before the answer stops mattering. which is a fair description of a language model. Trained to minimize cross-entropy, which is to say trained to compress. Scaling curves are compression curves. Loss falls, the file gets smaller, and the thing that fell out of it was an ability to hold a conversation, none of which says a language model is intelligent in whatever sense you care about. It says the objective it was trained against is the one this whole framework points at, which is a more specific claim and an easier one to check. There is a serious objection to all of this, and it deserves stating properly. Compression measures how well you account for what you have already seen. It says nothing about how fast you can handle something genuinely new. A system can compress a corpus beautifully and be helpless one step outside it. The sharpest version of the objection is that a system with enough parameters can compress by memorizing, and memorization and understanding are indistinguishable in the training distribution and completely distinguishable outside it. So the competing definition is not about description length at all. It is about efficiency, how much skill you acquire per unit of experience on tasks you were not built for. Under that definition, a child outperforms every system we have, and it is not close. The tasks built to test that are deliberately resistant to memorization. Each one is new, each has only a handful of examples, and the whole point is to measure how much prior knowledge you can bring to bear on something you have never seen. I do not think these are rivals, quite. One asks what a good model is, the other asks how cheaply you can find one. Compression is the target. Search under a budget is the difficulty. A theory of intelligence probably has to be a theory of both. There is a version of this where the two are formally connected through the amount of computation a program needs as well as its length, and that is roughly where the theory currently sits, promising and not yet finished. So, what is intelligence mathematically? The cleanest answer we have is that it is compression, finding the shortest description that still predicts. That answer is precise, it is provably optimal, and it cannot be computed. Which leaves the real question, the one the mathematics hands back to us. Not what the best model is, but how anything ever finds one in time. And there is something fitting about that as an ending. The mathematics gives a complete answer to the question as posed, and the answer turns out to be a description of something no one can build, which tells you the question was slightly the wrong one.